Hello, everyone. He said to me, "Do you want a full introduction?" I just said, "Just tell them it's the round trip time guy." So that's me. As I said, if you remember the first slide and the last slide, you've done very, very well. So don't worry too much about the rest. We talked about the Bristol clock this morning, if you remember. You can see there's the minute. I'm not sure actually it's at the station or the corn exchange. I got confused this morning, but there are 2 minute handles. You can see they're 11 minutes apart. One for the real time in Bristol and one for Greenwich Mean Time. Any guesses which one is the Greenwich Mean Time? 50 pence. The top one. Who said that? You said it? No, who said it?
Lutfi.
There you are. There's another £3. Okay, so it was a serious issue. Obviously, there were lots of accidents, and Bristol was the first place to start displaying Greenwich Mean Time in addition to local time. Or the other way around, actually. They were the first people to display the local time, their own local time. So you heard people talking. Janne talked about calculation and simulation today. Calculation is still used. I think there was a number. I was pleased to know that. But we do have actually the 2 extremes. We have the extreme of calculation, and Janne said these were for the simple buildings. And I think someone asked the question, how do you define a simple building? I think, and the most complicated building was simulation. Monte Carlo simulation is something that has started to move from calculation to keep on trying to find the value for the round trip time as we make conditions more similar to simulation. And I'll show you a slide at the end that explains that issue in more detail. So what is a round trip time? We still think of the round trip time. We have, if this is up peak only, this is actually the position of the lift in the building, and that's time. And we're actually doing a round trip and stopping, then expressing back because it's incoming traffic only back. And the time between this point and this point, or this point and this point, 2 identical points will actually give us the value of the round trip time. And as I said, it's still a powerful tool being used, but I think in its most simplistic form, it makes too many simple simplifications of the real life scenario. So Ben actually, he said to me, I'd really like to know what Monte Carlo simulation is. And I've been asked that questions many times. Let's try, actually, we'll do another competition. And let me ask you a question. Let's assume we have a building that has 10 entrances above the main floor. 1 entrance, 1 main entrance. 10 passengers arrive in every trip. I know it's a simplification, but we need to make that simplification so we can think of the possible scenarios. Start thinking these 10 passengers have arrived. The lift is there. It's opened its doors. It's equal populations on all floors. So any one of the passengers can go to any one of the floors. They are completely independent. So they're not actually influenced by anyone else in the group. They're not traveling in groups. Each one of the 10 will make his or her own decision. And every time what we do, we get the 10 passengers, we throw them in the lift, we close the doors, they make their selections out of the 10 floors, the lift goes, delivers them, and comes back. That time is the round trip time. How many scenarios can there be? Well, the first passenger can go to the first floor, the second passenger can go to the first floor, third can go to the 5th, and so on and so on. And then you might end up with the highest floor being 8. You might end up with 5 stops, so on. Yeah, you remember all of that. Let me ask you a question. What makes every one of those round trips different from the following round trip? Why aren't they all identical? What is the main source of randomness in this situation? We have 10 passengers every time, so P is not going to change. We have the same building and the same speed, the same opening time and closing time. What is making one round trip different to the next?
Destination.
Excellent. Who said destinations? Yeah, the destinations. So does anyone know how many combinations we have? Any ideas? More, much more. It's 10 to the 10. So it's 10 billion possibilities, 10 billion combinations. If we set a computer to try to calculate them, it will sit there forever. It will sit there literally for 2 hours calculating. So instead of trying to do the 10 billion, what we do, we throw a pair of dice for these 10 passengers once. We calculate the round trip time. We put that value to one side. We throw another pair of dice for the next 10 passengers. We calculate the round trip and we put it to one side. We might only do that 100 times. Isn't 100 times much less than 10 billion? That is what Monte Carlo simulation is. That's what it's trying to do. It's saying, let me draw a representative sample out of the 10 billion combination, which I'm never going to finish, and these 100 or 1,000 will be representative. Has that made it any clearer? Now, 2 questions. £1 or £2 each. So 10 passengers arrive at the main entrance and board the lift. Their choices are completely independent. So they're not traveling in batches, they're not traveling in groups. Because it's equal populations, what's the possibility that a passenger goes to the 5th floor? The probability? 1/10. What's the probability of 2 passengers going to the 5th floor? It becomes more complicated. It's actually more than 1/100th, because there are different ways of selecting. But it depends whether we say the same passenger or a group of passengers. But now let's ask the first question. Under what set of choices, and for £1, will the trip time, round trip time be minimal? Okay. Now the question, and you can answer me at the end. Under what set of conditions will the round trip time be maximal? Don't say anything now. We'll stop at the end, but you have to justify your answer. When will it be maximum? Do you realize now that the value of the round trip time is not constant? It's an average of 10 billion combinations. We always talked about the round trip time when we put it in capital letters, capital R, capital T, yes? And in mathematics, when you put something in capital letters, it's trying to imply to you it's constant. It's not constant. It's an average of 10,000 possibilities. If you try to run the 10,000 possibilities, you'll never finish. So what you do, you select a representative sample in Monte Carlo simulation, come up with a number. If you do 100, you'll get a better average if you do 1,000. You'll get a better average if you do, but you have to sample randomly. So I think this has set the scene a bit. So let's try to get into the 2 sources of randomness. You said destinations, the gentleman here. What is the other source of randomness? The main one is destinations. It's the main contributor to randomness. But there is another one. No, you're correct in what you're saying, but we fixed it in this experiment. We've put 10 every time. The combinations will be included in that.
Don't allow.
No, we're assuming that actually, okay, their behavior is slightly random, how they get in and out. But there is, these 10 passengers, what have I done? I've actually brought them at the same time. Yeah, they don't actually, in real time, they don't arrive at once. So if we want to think, if these 2 sources of randomness did not exist, then we would have the same round trip time repeating every time. But the 2 sources of randomness, the most important one was the destinations and the combinations they make, 10 billion in this case. And the second one is the way they arrive. They don't arrive tick, 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 tick. If they did, they'd make our life much easier and much better. But they arrive maybe 3, and then there's nothing. You go to a barber shop. I don't know what the barber shop. I looked at you and I thought of a barber shop.
I used to say what you do. Yeah.
But a sandwich shop, a barber shop, an electricity generating company would have that problem. Everyone wants to use the kettle and the electricity at 5 o'clock. 3 o'clock in the morning, no one is using. And that peakiness is what causes the problem. So the 2 sources of randomness. Richard suggested a third. Passenger origins and destinations. That's the main source. Passenger arrival time. Batch arrivals. Batch arrivals, when people actually arrive in 2s or 3s or 4s. That actually makes the life of the system easier rather than more complicated, because they usually go to the same destination. So they don't cause 2 different stops. But these are 2. Now, the previous paper I did 3 years ago took this into consideration. Today we're taking this into consideration, and I'm going to show you some results. So we talked about the two sources of randomness. Lambda is actually number of passenger arrivings per second. This is actually what I mean by you can see this would be an ideal world scenario, but that's not how passengers arrive. We assume that in the classical round-trip time calculations. This is how passengers actually arrive. So you have, and this is even less complicated than this, which is a Poisson arrival. And with a Poisson arrival, you can see sometimes we're really struggling to get any passengers through, which is not good, because the lift is sitting there waiting. And then later on, you get more passengers. You see these three? You see even these three and these two. This peakiness makes life much more difficult and more random. And we start losing handling capacity. So basically, the way to get 100 representative scenarios or trials out of 10 billion is to use correct random number generation. You really need a good random number generator to make this representative sample, or this sample representation of all the trials and scenarios. So Monte Carlo simulation started with the most basic case, which is incoming traffic, up peak. And then now it's being used to actually develop round-trip time for sectoring. So if we have a sectoring system, incoming traffic, outgoing traffic mix, multiple entrances, destination group control, and it shows you exactly what the value of the round-trip time is for destination group control. So the interlinked actually takes these scenarios to a more advanced level, and what it does, when we did the normal Monte Carlo simulation, there was a scenario. So you generate 10 passengers. They go into the lift. They select their destinations. You get the round trip, and that's it. You do another trial. With interlinked, we start linking one scenario to the next, one trial to the next. So we're starting to try to simulate more passengers waiting in queue, long interval, bunching, and so on. So the interlinked actually starts linking one of these scenarios to the next. And you can see, and what's happening now, instead of doing just 1,000, we're doing 100 trials over 1,000 times. So it becomes more compact in terms of interlinked Monte Carlo simulation. Let me show you some results. So this is actually 100 trials of Monte Carlo simulation to wait for things to settle, and what we're showing here is queue length. You can see now in calculation we could never talk about queue length. All we could come up with in calculation was the round trip time, and then get from there the handling capacity and so on. By starting to move from calculation to simulation, Monte Carlo simulation is allowing us to see what the queue length is, what the round trip time is, and then the handling capacity. And you can see a deterioration in the handling capacity when you start taking all these random factors into consideration. Let me conclude, and then I'll show you actually a practical application of this. So two sources of randomness were modeled: random passenger destinations, that was done last time, and random inter-arrival time between passenger arrivals. Both random effects have a deleterious effect. When we did calculation, everything was perfect. So we couldn't see actually the effect of these things on the value of the round trip time. So let's see a practical application. One of the things you can see here is this actually is settling down. And this is actually settling down. And this is settling down. So if I do enough scenarios, I can actually come up with a value for the queue length. I can come up with a value for the round trip time. I can come up with a value for the handling capacity. But I'm doing it now under interlinked conditions. So I'm taking into consideration more of the real life things that are happening. I need probably to go a bit longer to get those to settle finally and then take a value. So as in the classical way in calculation, we came up with a round trip time and a handling capacity. Now we can come up with a queue length and eventually come up with an average waiting time, average traveling time. Are we still in calculation? Have we moved towards simulation? Where are we in between? I'll show you a graph at the end which summarizes this. We okay for time? So this is actually a practical application. You might ask the question, in Monte Carlo simulation, what would the effect of the car capacity be? And this is actually assuming, because we have now fluctuations in the number of passengers. I think the gentleman, you mentioned the number of passengers. So in here, we're not assuming that we always have 10 passengers arriving. And we take into consideration that some passengers will be carried over from the previous trial. So we have passengers being carried over and a number of passengers. So now the car is actually critical, because if I have a car that can only take 10 passengers, if there are 11 passengers waiting, I've got to leave one passenger out. This is not something that was taken into consideration under pure calculation. It was assuming that 10 produce, 10 in, 10 produce, 10 in. And what you can see as well, as you start increasing the car capacity, you can see that the queue length starts dropping. So you can actually come up, and in fact, it's settled very nicely here. It's settled at a certain number here, smaller and smaller. So at 4 passengers extra capacity, we've probably eliminated the queue length. Now, I'm not necessarily saying you'll get the same result with simulation. Simulation is still taking more real-life events into calculation, but we have come very near to it. The final important slide is this. And this is calculation. This is pure simulation. These are the idealized conditions, constant arrival process. So people arriving tick, 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 tick. No bunching of elevators. No group control. Incoming traffic only. Single entrance. Equal one round trip. Full advanced knowledge of passenger destinations. Infinite processing power and so on. On this side you can see a passenger arrival process. Bunching. Effective group controller. Mixed traffic conditions. Multiple entrances. And as you start actually introducing more reality, you're moving in this direction. And this is a very nice summary of the difference between the two. So I'll just show the final slide and then we'll take the answers to the competition. So this is actually a serious quote. The generation of random numbers is too important to be left to chance. And it's actually quite serious. This is actually, you must be careful that you don't generate the same sequence, and you might actually end in that trap. If you don't change the seed at the beginning, you end up with the same sequence. So you can keep on getting similar results. So you have to really know that you're actually generating correct random numbers. Now, this is a completely different subject. I think we've got time just to talk in 1 minute and then, okay. So this is interesting. This is from hydrogen. We're doing some research on hydrogen, and in fact, I'm going to be in Germany next week. This is interesting because green hydrogen needs wind and solar combined to use it on an electrolyzer and produce green hydrogen. Now, you need enough hours in a year, 7,000 hours, so you need to move towards the red in areas of the world where this is feasible. So you can see probably in North Africa, areas in Africa, areas in the US, Somalia, Chile, Patagonia. These are areas where it's feasible to produce green hydrogen from renewable resources, because the number of hours, when you go to the blue areas, you're just not getting enough hours. It's not feasible. You're talking about the 3,000 hours a year, which is not feasible. There's a point to this, because if Europe needs green hydrogen, it's going to be difficult to produce it in Europe. So we have to transport the hydrogen either as hydrogen or a derivative of hydrogen to these areas. So hydrogen transportation becomes very, very important. Okay, I've finished. Thank you very much. Can I do the competition result? No? Okay. So anyone who's got the answers, just see me at 4:30. Thank you very much.
Okay. Thank you.